right, so we're going to look at a practice problem with getting to the nuances, the details of image formation in a spherical mirror in a mirror. We're going to use a concave mirror in this example, a converging mirror. And our example reads, imagine that you have an object. That object is 1.5 centimeters tall. And it is at a location 20 centimeters in front of a concave mirror. So our height of our object is 1.5 centimeters. The distance of our object from the mirror is 20 centimeters. That mirror has a radius of curvature of 30 centimeters. So there's a little bit of the details of our problem. Now this problem wants us to answer the question 1, what is the image location? Okay, so what are we thinking about there? Well, the distance of the image relative to the mirror. And part 2 is how tall is that image? Okay, and that of course is our image height. So we're interested in our image distance and our image height. Now, to find the details, location, and size of images with curved mirrors, we can actually use the same relationship as we did for lenses, the lens equation. And we talk about the details of that lens equation in a mini lecture on the lens equation, and I introduce in that mini lecture that it also works for mirrors, even add a little details about those mirrors. But let's just remind ourselves what the lens equation tells us. It relates the object distance and the image distance to the focal length. Okay, so 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. That is our lens maker's equation. And I'm interested in the object distance, so that's good. So I can solve for the object distance. Get 1 over the focal length minus 1 over the object distance, the image distance. Solve for that. I'm not given the focal length though. So how do I get the focal length in this relationship? Well, we want to keep in mind that the radius of curvature is related to the focal length. Remember, the focal length is equal to 1/2 the radius of curvature. So I do know my focal length. It's 15 centimeters. And I can use that to solve my problem. Now I'm going to take a little pause here and I want to remind you that image distance, object distance, and focal lengths all had positives and minuses related to them when we talked about the lens equation with lenses. The same is true in mirrors. So again, I would encourage you to go back and look at those relationships. When we are dealing with a converging situation, a converging mirror, which is a concave mirror, the focal length is positive. It's on the same side as the object. So you just imagine real quick, here's our concave mirror. If I put my object on this side, that curvature, I'm going to have my radius of curvature and I'm going to have my focal length. That focal length is the same side as the object. That is one indication for us of our focal length being positive. And so, more importantly, think about it as being converging. So converging mirrors give us a positive focal length. So this is, in fact, a positive 15. All right, I'm going to solve for this. I have 1 over the distance of the object is equal to 1 over 15 centimeters minus 1 over 20 centimeters. Now, I don't have to convert this to meters because everything is in the same unit. And if I go ahead and solve for that, I end up with an image distance equal to 60 centimeters. So 0.6 meters, 60 centimeters. Now it's positive. What does that tell us? A positive image distance tells us that the image is on the same side as the object. Does that make sense? We learned in our conceptual description of image formation in a curved mirror, and go back and look at those mini lectures, or the ray tracing will also tell you that mini lecture, that if I have my object either outside the radius of curvature or between the radius and curvature and the focal point, so in all cases further away of the mirror than the focal point, then I create a real image. And that real image is on the same side of the mirror as the object. Well, my focal length is 15 centimeters and my object is at 20 centimeters. Now my radius of curvature is 30, but the object is in fact in between, so if it's going to represent this object in this example, that object is in fact in between the radius of curvature and the focal point. So I expect a real image, and I expect it to be on the same side as the mirror. I get a distance of my object is positive. That gives me that affirmation that what I expect is what is indeed happening. All right. The second part of the question says, how tall is this image? How tall is the image? That has to do with magnification. Remember, if the lenses, our magnification was equal to the height of the object the height of the image relative to the object. And we found through some of the geometry manipulation, you can go ahead and look that up in your book, that this is minus the height of the distance, of the image relative to the distance of the object. Well, now I have the distance of the image minus 60. I have the distance of the object, which is 20, and I get my magnification of minus 3 for magnification. Now, what does the minus tell us? Well, the minus, remember, tells us that the image is upside down. That means it's a real image. Is that what I would have expected out of this converging concave mirror? Yeah. Unless I'm inside the focal point, I'd expect a real image, same side of the mirror as my object. So it's going to be upside down, and therefore that tells us it's real. All right, so using the lens equation in our mirror situation, we can also use it for convex mirrors, keeping in mind that the focal point of a convex mirror is on the other side of the lens. It's diverging. The other side of the mirror, it's diverging. And we should see that that focal point then must be negative, and that should give rise to the expectations we have for the object distance and the height. All right, good job.